So welcome to all the participants of this first webinar of the CLARA Project webinar series. My name is Stefano Bagli. I'm the CEO and founder of Ecosistema, an environmental engineering company based in Italy. Ecosistema is partner of CLARA Project, an Horizon 2020 Research Innovation Action. And the name of CLARA, of the project, is to develop a set of climate services building upon the recent Copernicus Climate Change Services, in particular exploiting the near-term forecast and the sectoral information system. And CLARA wants also to sustain the marketability and the value of the developed climate services. So the project is almost at the end of the life, and in this series of 6 webinars, we will present the 14 developed climate services organized in 6 webinars in 6 sectors. So basically, today we have a presentation of the services related to flood risk. And the 15th of October, we will have more focus on water management, then agriculture and irrigation, energy, the 19th of November, and finally we will have the last 2 focus on air quality and climate data. So the total duration of the webinar is between 1 hour approximately, and we have the presentation of Mattia Madio of duration of 30 minutes, and the rest of the time is available for a Q&A session. So please use the question menu to add and write down your question to the presenter. So the last slide is just to remind that this webinar will be recorded and uploaded to the CMCC YouTube channel. You can have here the details. Anyway, if you have some question or doubts, please contact the CMCC through this webinar email. So I will like to give the floor and the microphone to Mattia Madio. Mattia Madio has a PhD in Science and Management of Climate Change, and he works at CMCC in Venice at the RAS division. And he will present us the climate services developed for flood risk assessment. So please, Mattia, I give you the microphone. Thanks.
Thank you, Stefano. I will start briefly by introducing the place where I do the research. So CMCC, the Euro-Mediterranean Center on Climate Change, is a non-profit organization established in 2005. In 2015, it became a foundation, and its objective is to research climate change and its interactions with the environment, the society, the world, the business, and of course the policymaker. So stimulate sustainable growth, protect the environment, and develop strategies for the adaptation and mitigation of climate change. The center has 7 different centers. Sorry, 7 locations distributed in Lecce, Bologna, Capua, Milano, Sassari, Venezia, and Viterbo, which involves connect public and private entities working together on multidisciplinary studies concerning issues of interest to the climate science. There are several different divisions that work on different topics. So 9 division, I work for the risk assessment and adaptation strategy, RAS. And so we perform analysis useful for disaster risk management and adaptation. There are several different topics. So the today presentation will touch basically on hydrogeology and adaptation and basically computing of risk modeling. So there are several outreach produced by the CMCC, publication, events, education events, communication, and of course publication of research papers. So let me start with the topic of today's seminar, which is FloodMage, a service which is aimed to the administrations in order to understand what is the current risk associated with flood events and the future development of this risk due to climate change. It is a scalable and modular service, and it wants to estimate both the direct damage and the indirect losses triggered by flood phenomena that may be river floods, can be pluvial floods, or coastal floods. The service is able to downscale the climate prediction to a local, regional scale, providing insights on how the climate variability will affect the final output of the damage. The modeling framework behind the service is made of 4 main components. The first one is the flood hazard modeling. So the hazard component begins by producing downscaled climate projections from large-scale models, so from global models, in order to obtain usable input for the flood and the inundation models that perform the actual calculation of how the water distribute over the land according to the rules set by these models. And the output, which have the form of hazard maps, have been are validated and compared with available records from past hazard events. And so from this we obtain these kind of maps that are combined together with a model of exposure that it's a representation of what value is located on the territory, on the area of application. So that combines the definition of land use and building categories together with the values obtained from local and national statistics, and the economic value connected with the type of building, maybe commercial, industrial, or residential asset. These 2 components are the input for the first model, for the first vulnerability model, which is a model that can perform an assessment of the direct economic impact over the exposed categories. So it uses a combination of descriptive variables and produce an estimate of the share of the total value of the building or land cover that can be impacted. So over the 100% of the value of an asset, we can estimate how much will be impacted by a specific scenario. So a scenario is tied to a probability, which can be estimated on the basis of observed records. The direct impact serves as an input for the macroeconomic model, which is a regionalized, computable general equilibrium model that can evaluate how the impact on a location can spread over the regional economy and to other regions. These 2 information are combined in order to provide an overall estimate of seasonal or annual damage, both in terms of direct and indirect financial losses. The first component, as I said, is the climate downscaling, which is a complex operation that requires a series of different tools in order to be applied. FloodMage relies on CS tools, which is a collection of instruments produced under Project Medscope in collaboration with CMCC. But of course, the reliability of the downscaling depends on the distance covered by the process itself. So uncertainty increases from further time scale to more local and close near in time projections. The tool has been already released but it will have a new version released by the end of October that include new interesting instruments, among them analogs, calibration, and others. We'll briefly introduce a few of them. So the analysis of climate analogs allow to identify which events and which days in the past have a similar characteristic in terms of climate indicators to the one produced by the forecast. So it can tell you how much similar the future is to the past, and it estimates by minimum distance from the forecast to the observation for the investigated climate variables, let's say precipitation. Then there is a tool that can allow to distribute the precipitation from a very coarse grid to a fine resolution, like 1 kilometer, accounting for the morphology of the land. In particular, this is aimed for application on mountain areas. So it considers orography, and it can distribute the water accordingly. The third tool I briefly introduce is the quantile mapping for bias correction, which is based on a nonlinear approach. The function computes the dynamical properties of the attractor and estimate how much the forecast is in agreement with observed distribution. As I said, these are the first input we need, and then I'm going to explain for each one of the flood phenomena the tools, the specific tools that are applied to simulate the inundation. So for fluvial hazard, we have a couple of different approaches. One is static modeling, which performs a simple binary classification of potentially flood-prone areas and identify exactly what are the priorities area where the water can accumulate and create an impact. Then we have dynamic modeling. We are experimenting right now. So we have both least flood floodplain, which is a well-known model for this kind of application, and Anuga, which is a free model we are learning to use right now that can both simulate rivers and canals inundation as well as coastal inundation. For the pluvial hazards, so for the flash floods, so those events that are localized in one area in a short period of time, we use a fill and spill model, which is a simplified model that account for the morphology of the territory. So the digital elevation model can provide the information where there are sinks, and so where the water can flow from one cell to the other and accumulate, and so in this way produce a map of maximum water depth. Finally, for coastal inundation modeling, we rely on input from European simulation. So least coast model provide the input for the sea level rise and the extreme sea levels, and this is projected. So we have the value of sea level rise out of the coast, and we project how this will impact the coast by adding the dynamic of the event. So we are able to simulate the momentum and the push of the water during hours. So it's not a static model. It can provide information about speed and duration, etc. Our area of application, our pilot is Rimini. Rimini has suffered from different types of flood events, so that makes it a good candidate for our test. First, we have an important flash flood happened in 2013, which costed 8 million euro of damage and 2 casualties. And we have a storm that impacted the whole Romagna coast in 2015. These events are the most recent, so also the one that can provide the best observations and can be used to understand if our modeling works or not, basically. We use observation obtained from the ARPAI network. So we have several stations for rainfall, for river discharge, for sea level, and for wave peak. However, the length of the record is varied. So for some phenomena we have much longer observation, but yeah, not more than 15-20 years. So that can be applied, but again, there is a level of uncertainty since we would need much longer records in order to validate properly the tool. I will start with a demonstration of the coastal inundation hazard because it's the one we are working right now. So it's the one we are currently performing tests on and producing the first result. Coastal hazard is affected more by wind and tides and storm surge than precipitation extremes. So that's why we are not using the precipitation downscaling I introduced before, but rather we choose to use the most recent and advanced regional Mediterranean modeling of the sea level change. But we want to increase its value, so improve its reliability by adding other information that are not directly accounted, such as the vertical land movement. We know that the region of the high Adriatic is subject to fast subsidence, and so we wanted to account this information, which is especially relevant for future scenarios up to 2050-2100. So we improved the input provided by LISCOS by adding this estimate, and we used ANUGA on a high resolution LIDAR, 2-meter LIDAR, and we've been able to compute the water surface, the bed elevation, and the wave momentum. I'm going to show you some preliminary results, which are from yesterday night. So these are as fresh as you can get. We have here a simulation of RP100. So we have a mean sea level of about 30 centimeter rise plus a storm surge event over 12 hours plus the momentum given by the wave, and we can see how the water flow within the city from the harbor area. We used to we had the chance to implement also a future change that will be made for the area. So we implemented the Parco del Mare, which is a new walking strip that is located along the southern shore. So we see that this new project will partially block the flowing of water from the coast. However, we can simulate that the water will find other ways to flow in from low-lying areas. So this is the first observation we are able to produce. While the production, when we release other scenarios, we are able to also estimate the risk and provide a more complete assessment. These are preliminary results for the rainfall modeling. So the fill and spill model, we try to simulate an event that resembles the condition of the 2013 flash flood. So these are the preliminary results in terms of areas that are impacted. We can identify which are the areas that are more impacted, where the water is reach higher depths. But yet this model requires more calibration because we are not currently accounting for drainage. So even if it's true that in short-lived events the urban drainage is often overwhelmed by the quantity of water, we have to find the right tuning, the right setup and because actually we are currently overestimating the extension and the damage connected with this event. So this is something that will be fixed in the next few months. River flood scenarios are the ones that are a bit behind the schedule, so we are trying to experiment with FAS inputs. So we have some already downscaled estimation of discharge for Italy, which has a nice resolution, and this can be used as input for the static GFI model that actually appear to perform pretty well compared to other products such as the hazard maps from JRC. But we also want to try implement a proper dynamic 2D model. So Anuga will be tested also for this kind of application. We are coming close to the end, so I will go to the damage model, the one that actually translate the intensity and of the hazard into an economic estimate. The first one is a multivariable model. That means that accounts for several characterization of both the hazard event and the exposed value. So we have water depth as the most important variables to account, but also velocity and other that are extracted from statistic can help to differentiate the degree of damage that each individual building suffer. Once we have this input, we combine it with the impact distributed over the GDP. The GDP is specialized using spatial proxies, so using land cover identification of industrial areas, agricultural areas, and urban areas where most services are located. And so we use this to feed the computable general equilibrium model that will tell us how this shock in one location of a region will spread along the whole region, and how this will impact the exchanges of labor and capital with other regions on the long time. The goals and challenges are currently what I explained. So we are waiting to perform a proper exercise using the input of the newly developed climate service tools, and that is going to happen during the month of October and November. They are already independently tested and validated by in-cast analysis, so they don't require an additional validation. However, both the hazard modeling and the risk modeling will have an application in comparison with historical events. Cost and risk methods and analysis are expected to finish by the end of the month, so we should have enough output for the area of Rimini, but also we want to apply the method to the other areas such as Monterosso, Laguna of Venice, and Taranto, and the results will be presented as a scientific article. The Pluvial risk model will be under refinement as well during these next few months, and will be calibrated over available hazard observation. And finally, by the end of the year, we aim to test Anuga for 2D dynamic floodplain modeling. So I think that I'm within time, and thank you for your attention. I will now shift to your question if you have any. Thank you.
Thank you, Mattia, for your excellent presentation. So now I think we have 20 minutes for a Q&A session. In the meanwhile, all the attendees will try to add their question to the system. I've seen that we have one question. I will start with a simple question. So we have seen that we are working with a city, the Rimini local administration, but which are the customers and the potential end user that could benefit from FloodMage climate services? Do we have other contacts? Are you working with other stakeholders? And
administration are usually the most interested, because when we talk about flood impacts, so we know that is the region that pays for compensation, but also insurers may be interested in applying this service. Of course, because there is a downscaling behind this service, we know that it's hard to downscale from very large projection to one building or 2 square kilometers. So of course we have to account the feasibility of the model, and this is why the model is tailored to the user. A preliminary encounter with the interested user is aimed to understand the feasibility of the model for the area of application and for the scope and the interest of the user. So the user may be interested more in a specific aspect or a specific impact category, and this is the strong value of the service compared to other products that are standardized maybe for the whole country or the whole globe.
Okay, thanks. So we have a question from Barrett Moore. So it basically is focused on land cover classification. So what land cover classification maps do you use? So there are many types of land cover classification. Are you doing the classification by yourself, or you are using some pre-processed?
No, we start from official data. So the one I'm showing right now, it's a combination of several data sets produced at the local level. So we have the land cover that identifies the type of area, maybe urban, industrial, agricultural, and over the land cover we have each individual building feature. So we have very detailed representation and very updated. I think it's the 4th level of classification of core inland cover. So it's a widely known descriptors. It's the same that is used at the European level, and this also helps the scalability of the model by using the same types and classifications.
Okay, excellent. I have a question related to the land cover. So in your modeling chain, which is the role of land cover in the infiltration, in assessing the infiltration, and in characterizing the value for the damage assessment? Which are the main role of the land cover?
Basically, the land cover and asset identification is meant for the risk component to understand what is the maximum value in that exact location, and so translate the maximum depth or velocity and duration into a percentage of the damage over the total value of the building. So, but also the definition of land cover can be used to improve some of the other models. For example, we know that where we have sealed surfaces, so asphalt built up areas, we have more water flow runoff, so faster runoff and faster water accumulation, while in vegetated areas we have some kind of absorption, so part of the flow is lost due to absorption of the soil, and so the hazard is partially mitigated. We try to account also for this component within our modeling framework.
Thank you. So thanks, Elena Di Pirro. We have another question related to direct damage assessment. What do you mean with exposed value and hazard features?
Okay, and that is exactly what I just mentioned. So the hazard features represent the characteristic of the event of the scenario we are simulating. So the hypothetical scenario with a fixed frequency, let's say, potentially can happen once every 10 years or once every 100 years. The features describe the input that are used by the model. So in practice, it's the water depth, which is the main driver of damage, and water velocity, if it's a dynamic model that can simulate water velocity, and water duration, if again it's a dynamic model. So basically, the most common description of hazard features is water depth. Water depth on a grid, so a raster layer that represents for each square meter how much water can accumulate during an event. The exposure value, the exposure feature, is the combination of geodata, so the geometry of the impacted area, and the statistics obtained from official records such as ISTAT or other catalogs that can describe, for example, the type of building, the quality of the building, the material of the building, how many floors the building has, if it has a basement, how many people live in that building. So that is useful to better characterize the degree of impact that can happen in that particular location, and that can vary for each building and for each area.
Okay, thank you. So in the meanwhile, we are waiting new question from the audience. I have another question for you. So you have experienced and tested several hazard modeling approaches. So the simplified and the more sophisticated and numerical one. So in terms of computational effort, which are the advantages of the simplified approaches? And another question, if you believe that in terms of validation, the simplified approaches, the raster base, can provide you good enough data in order to assess the risk?
Well, the advantage of the static modeling over the dynamic modeling, of course, is the time required to set up the model and to run it. For example, the dynamic modeling of waves requires twice the time of the real event. So for a 10-hour event, we require 20-hour simulation. And while the static modeling can perform almost instant assessment, provided that the setup behind the model is correct. So the DTM and all the variables that fits the model. Say that the service does not aim to provide early warning system, so that is not meant for nowcast and from near real-time applications. Even if some of the components of the model can be very fast in providing the results, such as the fill and spill model, that is not meant for early warning system.
Okay, so we have a question from Andras Toth. So what kind of climate model do you use for future estimates? Could your model be used by EU member state in the preparation of flood hazard and risk maps? Two questions.
Yes, I mean, the input for the climate simulation are the one produced by CMCC and other important climate research centers. So usually it's an ensemble of different models that are weighted, and then we obtain one composite input that is used to start the downscaling procedure. So the models are the one currently more developed and more advanced. What was the second part of the question? Sorry.
Could your model be used by EU member states in the preparation of flood hazard and risk maps?
Yes, of course, and that can be one of the application of the service. So if one administration wants to provide updated hazard maps for their flood management plans, they can ask for it. They can come to us and specify their requirements, what they need, which kind of scenarios they want to implement, and we can perform a feasibility analysis in order to see what of the requirements of the user can be provided by the model, by the service.
Okay, thanks, Mattia. I don't know if there are other questions. I cannot see from the question list. So we have still a little bit of time. So I strongly encourage people who has some doubts or want to add their question to type in the question panel. And I have another question for you. So actually, you are working with the city of Rimini. You have some plans in order to apply the same methodology to other urban areas or other region in Europe? Which are your future plan?
So yes, indeed, the current plan. I mean, as I said before, the current development is the coastal hazard. So we are writing a paper on 4 Italian locations, but our objective is to also include the non-Italian pilot areas. We started with Italy because, of course, we already have a lot of data, and some of these pilots have been partially developed during previous research studies. Yeah, our objective is to produce more and more examples, more and more demonstrator, and at different scales with different objectives in order to communicate to the user that this service is able to adapt and transform to their requirements.
Okay, thank you. So I cannot see other question. I have my last question. So we have seen all your modeling chain. How will be deployed this kind of climate services? Are you thinking to develop a sort of application that could be available for also external for all the interested people, or is more focused on deploying the services as a consultancy services or a research project service? Which are your plans?
So it can be both. We don't have to, in our plans, we don't have a platform, so we don't plan to have an online page or an online demonstrator to show our results. So the results are provided, the output of the service are provided in a consultancy like fashion. So in terms of hazard maps, in terms of reports, in terms of charts and spreadsheets, including all the numbers of produced by the models, together with an explanation which is aimed to the technicians working for administration, or anyway the technical side of the user. So the facility of access is limited by the understanding of how the output is produced, and what the output is and what it's not, what it should be used for. And for all these reasons, we prefer to have this kind of approach, because the user need to have the correct understanding of the reliability and the uncertainty connected to the data produced, and the objective for what the data are made for. And we think that by releasing it just releasing a visual output on a web platform will get some of this value lost.
Okay, we have another question again from Helena. Thanks, Helena Di Pirro. So the different models all to rank each land use with different capability to water drainage, or is based on empirical data? So I think it's related to the infiltration capacity related to the land use. So which data do you use to assess, I think, if I well understood, the infiltration capacity related to land use?
Yeah, these are obtained from literature. So for the as well as the subsidence rates, any local data we can put our hands on is used to characterize the local application. So if there is proper data from that area that help to give a value to each type of land cover and water absorption, we are going to use those. If there is no specific data produced for that area. We are going to use more general data maybe for the region. If data for the region are not available, then we are going to use another data which may be less reliable, but the point is we are trying to keep the scientific credibility, so whenever there is no data available to implement some particular advanced function, we have to be honest and say this data is not enough to perform this kind of assessment, so we have much more uncertainty because of this. And this is also a part of the output and why there is a report connected with the analysis produced by the service.
Okay. So if there are no other questions, I will like to say thanks to Mattia for their excellent presentation and the ability to answer to all the questions. And I would like also to say thank you to all the attendees. And so see you for the next webinar series of CLARA that is planned the 15th of October and will be related to climate change projection and water management. So thank you again, everybody, and I wish you a good day.
Thank you to the audience. I'm available for any clarification. You can write my email, which is mattia.amadio@cmcc.it. Thank you and bye-bye.